Hello, my name is Evan Gillette. I'm the project manager for the Flapping Wing Micro Air Vehicle project. To my left is Alex Lopez, who's the team lead, and this is our Fall 2019 team presentation. So to start off, a little bit about our project is that we're a graduate and undergraduate research team under Dr. Taha, one of his field of research is unsteady aerodynamic systems. So a few examples of unsteady aerodynamic systems would be the hummingbird and the dragonfly. And they use something known as non-conventional lift generation, which is different from conventional lift generation, which would be something like a fixed-wing rotary propeller. And these biological systems of achieving flight is the inspiration for our project. They're able to maintain stable flight through something known as vibrational stability, which allows for traditionally unstable systems to become stable without the aid of controls.
The overall research goal of our project is to develop a micro air vehicle that derives thrust and stability from flapping wing mechanisms and explore the flight dynamics that make such flight possible.
So a few of our team objectives were made up of two teams, the quad flapper team and the systems identification team. For the quad flapper team, our main objective, two of them, are to discover and demonstrate the advantages that flapping wing flight or non-conventional flight might have over conventional flight through the demonstration of comparisons between a quad flapper and equaling a quadcopter. And our second goal is to design and manufacture a micro air vehicle which satisfies DARPA's requirements of being less than 15 centimeters in each principal direction. And both of these quad flappers will derive their lift and thrust through flapping wing mechanisms. Here's a quick video of our quad flapper flying. You can see it uses 4 ornithopter designs for flapping wings to generate its thrust and lift.
For systems identification, some of the team objectives are to develop mathematical models behind flapping wing flight and to design and manufacture test experiments for flapping wing mechanism analysis. The way we do this is through slow motion video using a fog machine and laser to visualize flow fields, and also complex equipment such as particle image velocimetry.
So here's our timeline for both of these teams. First, for quad flapper team, our first goal, which was to compare the quad flapper to the quadcopter, would require the design of a speed test, which our milestone that we were aiming for was week 10 to complete the final design with accuracy within 1 centimeter per second. Our second goal, which was to design the tiny micro air vehicle version. Our milestone that we were aiming for was to achieve liftoff, and we were able to do that in week 8. It was able to fly about 1 foot off the ground, 1.5 feet off the ground. It couldn't go any higher due to the ground effect, which is basically a blanket of air that forms underneath the vehicle that adds to the lift component.
The timeline for systems identification include having 6 base locking values by week 10, and also having a low-slope prototype by week 10, also using Arduino.
So a few of the design requirements for the quad flapper, in order to compare the quad flapper vehicle that we have now to an equivalent quadcopter, they would need to have equivalent weights, which we've determined to be within 0.2 grams. And they will also use identical structural and control hardware, which would be like the wing arms, the centerpiece mounts, and the flight controller. And the first comparison test that we'll be doing is testing the cruising speed at 50% throttle. And the speeds for our design in the test, it'll have to be accurate to within 1 centimeter per second. Secondly, for the micro air vehicle, we'd like it to be able to sustain stable flight 1.5 meters above the ground for 60 seconds. And to quantify stability, we've determined that it'll have to stay within a 1 meter cubed volume without the aid of user input to keep it from drifting outside.
For systems identification, the requirements include finding the instantaneous flow fields at different points of the wing cycle. This includes phase locking at 0%, 20%, 40%, 50%, 60%, and 80% of a flapping wing cycle, and to measure the dynamic forces such as lift and thrust with a sampling rate of above 1,000 Hertz in order to supplement flow field data.
So the progress that we've made this quarter, like I said before, our micro-air vehicle was able to achieve liftoff, which was the first milestone in determining whether our design is validated. And second, the quadcopter was designed and manufactured, and it's ready to be conducted for the speed test, and the speed test prototype has been finished.
For systems identification, here are some of the images for the PID team. We've successfully phase locked using a laser and photoresistor. The graphs here show the resistance of the photoresistor changing when the wing goes over the laser. Here is the actual test rig, and here is the actual images from the PID system itself. The images shown below here are taken using a fog machine and laser sheet, and the images are ripped from a slow motion video. You were able to find the picture, the vortices and jets at different parts of the wing cycle, and compare how efficient they were to different designs of a flapping wing.
So, to summarize our project, we were able to observe nature to see how they sort of make sense of this non-conventional lift generation and being able to achieve stable flight using systems that are time varying and non-linear. We were able to recreate that in a lab setting with a 2-degree of freedom pendulum to demonstrate this vibrational stability phenomenon. And then from there, we go into engineering application for designing a quad flapper, and that leaves the future.